Hello, this is Clayton Weiss with Mind of Its Own Design. Today I'm going to be answering the question, how is it possible that you can, as a human being, strong as you might be personally, no offense, how is it possible that a human being can break a piece of steel, even as small as a paperclip or a bobby pin? I mean, have you experienced this before where you have a paperclip, you straighten it out, you bend it back and forth a bunch of times in the same spot, and then it breaks? Why is that? How is that? How does it change by just repetitive motion? Repetitive motion leads to it stiffens up, it heats up, and then it breaks all at once. It doesn't stretch out. I'm going to show you right here. Now it takes a few cycles. This is a bobby pin. I don't have a paper clip right now, but bobby pins are even thicker and they're made of steel, just as paper clips are. So it's still a good example. To be patient. And there it is. Broke it. Now, each individual bond of the metal is so strong. A single bond, it's hard to even imagine you can break it. Inside of many common metals and elements, what exists a crystal structure. A crystal structure is an arrangement of the atoms that this element or compound or alloy, in this case of steel, is iron and carbon. Now, these atoms, it's best to think of them as spheres. They're very small, but they're round. They're round spheres. So, there's more to get into on that, but in practical terms, you think of them as like a ping pong ball. Think of them as ping pong balls. Now, if you're going to stack spheres or ball-shaped objects, you could just say we're going to pour a bunch of ping pong balls into a milk crate. You could just pour them in, and you'll get some number that'll fit in. But if you really want to fit the most number of ping pong balls, you have to put them in a certain order and configuration. So the closest stacking of spheres is one sphere with 6 around, and that goes on in every direction. 6 surrounding each, and that's one layer of atoms, in this case of iron. Now, if you want to put another layer of atoms in, you could stack them here, 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 here. That is to say, you could stack them in alternating spots. Long story short on this, even though you look at a piece of metal and you think, it's the same all the way through, I mean, it's one piece. It's actually made up of millions or billions of atoms. These atoms have a particular shape, and the connection between them, or bond strength, is extremely potent. In metals, electrons are shared throughout many different, basically all of the atoms in a metal that are connected electrically conductive will share outer shell electrons. Now, this is called a electronic bond, metallic bond, excuse me. So, anyways, the point is they're bonded together, but they're also spheres. So, do you guys remember this puzzle it's like a old-timey puzzle? Maybe you would get it in one of a quarter-operated vending machine. It comes out of an egg, and it would be a picture of maybe a face or a landscape or whatever, any picture, and it's made up of a bunch of tiles in rows. Right? And only one of them is missing, and you have to slide each puzzle piece one at a time. You slide them all, slide, 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 and gradually you move this. You can move this piece, you can move it, you can move that missing piece. You just have to do it one move at a time. So, how does this relate to metal bending and then ultimately breaking? The answer is what's called a dislocation. Now, atoms in metal and many other things that form crystals, which is an orderly pattern to the atoms. So many elements, most elements, and most ceramics, metals, some plastics, and things like minerals and quartz, things like that. Those all have periodic, repeatable crystal structures. When you have such a thing, and many, many, many atoms are stacked up, you can actually use an electron microscope to visualize stacks of atoms in a transmission electron microscope. And from that, we've learned that these atoms, it is good to think of them as spheres, number one. And number two, these dislocations, which is, in short, it's a missing row of atoms where the bonds in the two layers of atoms are warped. And in this warping, to accommodate a number of atom change from layer to layer. So it's kind of like this. Now let's say you have your stacking of atoms. Right? That's a close packing of atoms. Now, but if you're missing So you're going from 7 atoms to 6 atoms. Now, what happens if there's one missing? Does the metal cease to be? Does it disappear? No, it accommodates it, actually. So you end up getting this, what's called a vacancy, in the lattice, or the crystal lattice. Now, those vacancies can extend way far in the direction. See if this is a 3D. You can have a row of vacant atoms running into, that's supposed to be going into the page, or into the metal. When you have this row of atoms missing, it acts like the metal version of this puzzle, in which you can actually move the atoms around that vacancy much more easily than you can just ripping them all apart at once. That's why you can't just take the metal first time and break it. You have to cycle it, fatigue it, because what you're doing when you do that is you're creating dislocation lines that extend throughout the metal. More are generated with what's called plastic deformation, where you're changing the shape of something, but it's not like a spring where it goes back to its original shape. It's a new shape. It's a totally new shape. When you have plastic deformation like that, you build up dislocations. The more dislocations you have, you get brittleness, you get internal resistance, they start interfering with each other, you generate more, but certain parts of the crystal will stop them, so they get built up at certain internal points inside of the metal, and at a certain point, it's too much, and that's why it takes many cycles, but ultimately it's a catastrophic failure because you've built up too many vacancies, you've built up too many dislocations, basically imperfections, and it becomes more rigid for the atoms to move against each other. And at a certain point, when you don't have any elasticity and you don't have any plasticity, it breaks. And so that's why you can break a piece of metal with your bare hands. Use this power responsibly. Please like and subscribe, and check out mindofitsowndesign.com. Thank you. Think about it.